messages from topics. Consumers can be organized into groups. Each consumer group can subscribe to multiple topics and maintain its own consuming offsets. For example, we can group consumers by use cases, one group for billing and the other for accounting. The instances in the same group can consume traffic in parallel. Consumer group 1 subscribes to topic A, consumer group 2 subscribes to topic A and B. Topic A is subscribed by both consumer group 1 and group 2, which means the same message is consumed by by multiple consumers. This pattern supports the subscribe publish model. Um, Anything to discuss here? I think it's kind of straightforward right now.
Yeah, can anyone explain like this point, like topic A is subscribed by both consumer group 1 and consumer group 2, which means the same message is consumed by multiple consumer.
So the message is there in the queue, and then like publish, I publish the message in the queue, and then the same message, and like unlike point to point where you have one message being consumed by one consumer, here we have like multiple consumers consuming the same messages.
Yeah, that my question is slightly related to the consumer group part. Like what does it mean by consuming with consumer groups?
Like, uh, so let's say there's a topic like whoever is the consumer who have the access to that topic is basically able to consume that message, and then like basically who are part of that group will be able to read the message.
No, so that's slight partially correct. What I mean to say was, I'm just reframing your word or rephrasing your word. Consider that two separate services has the access to the to one topic, or like one topic is giving its access to two separate type of services. That's it.
Hmm.
So they took this use case thing, right? So for billing and accounting, let's say I am let's say I'm building a e-commerce pipeline, and in e-commerce pipeline, if there is just one server trying to just dequeue all the order that are placed. So for order management, I'm building a queue. If a particular order needs to be also shown in the front end, same order needs to be also processed in through payment service, and same order should also be sent to some sort of a billing thing. Billing means like some sort of a accounting like financial billing or financial accounting stuff. So these three so the same order needs to go or the same transaction needs to go all three places. That's something like consumer group. Like billing consumer group consume one particular order, same order could be consumed by accounting, and same order could be consumed by front end rendering or like front end service. Sorry.
You're
Uh,
not audible.
so I'm saying it could be or it has to be consumed in the same order by all the three services.
Yeah, that's a yeah, order comes later. Like order is a like a second like that. So right now we haven't yet started discussing about the order part,
Okay.
but uh, like I'm just trying to point or highlight like what exactly means by consumer groups, and then in consumer group we will see how the order is preserved. But at the first place, I'm trying to ensure whether everyone understands what the consumer groups are, like, because it's slightly consuming it's slightly confusing. uh, like, consumer group is different than the individual consumer itself in each consumer group. So
And what can be the example for consumer group 1, in that we have consumer 1, consumer 2? How we can relate to at like normal, like how you explained for two services. Inside consumer group, we can have multiple consumers. So that I understand, but application point of view or normal.
is this
Uh,
workers, right? One service can have 10 workers, or like, let's say, basically some sort of like parallel instance.
okay.
Say one billing service is like, it's a very high scale service, and you have 10 horizontally scaled servers handling the billing service.
Okay. Thank you.
Does that help everyone? Feel free to clarify this, because the following discussion would definitely gonna be very confusing if you don't understand what are the consumer groups. Does everyone understand? Like, uh,
Yes, yeah. Actually, yeah, I'm not from. I do not have the Kafka background. This or the message queues background, but this really helps
perfect,
understand what it is.
perfect, perfect. Sounds good. So let's go ahead. If anyone has any doubt, feel free to interrupt. Okay, Sim.
However, there is one problem. Reading data in parallel improves the throughput, but the consumption order of message in the same partition cannot be guaranteed. For example, if consumer 1 and consumer 2 both read from partition 1, we will not be able to guarantee the message consumption order in partition 1. Uh, what does it mean by like it won't be able to guarantee the message consumption order?
Yeah.
Um,
So, go ahead.
no, I was just saying we can read the next paragraph as well, and then I think
Yeah, okay.
we would be able to, yeah, make more sense.
The good news is we can fix this by adding a constraint that a single partition can only be consumed by one consumer in the same group. If the number of consumers of a group is larger than the number of partitions of a topic, some consumers will not get data from this topic. For example, figure 4.7, the consumer 3 in consumer group 2 cannot consume message from topic B because it is consumed by consumer 4 in the same consumer group already. With this constraint, if we put all consumers in the same consumer group, then the messages in the same partition are consumed by only one consumer, which is equivalent to the point-to-point model. Since a partition is the smallest storage unit, we can allocate enough partition in advance to avoid the need to dynamically increase the number of partitions. To handle high scale, we just need to add consumers.
Yeah, Sagar, can you explain now? Like, what is it trying to say?
Yeah. So consider the order, like, one scenario that comes to my mind is, consider like, there is this order management topic or the order topic, and a billing service has, let's say, five replicas or three workers. All three workers are trying to consume a particular order, and let's say the order are numbered 1 2 3 4. So possibility is like, the first message could be read by all three workers. The first order is read by all three workers. Chances are that for the second message, only worker 1 and 2 reads it, and 3 doesn't read it. And again for the third message, let's say third fourth message, worker 1 reads it, acknowledges it, but 2 and 3 worker were busy. So the next message, next message that 2 and 3 reads is directly 5 or 7. So there could be this kind of chaos that could happen, right? Like unorderliness that could happen if multiple consumers or multiple workers of billing service are trying to read or trying to pick into into the same topic partition. So there could be race conditions, there could be duplicated race condition. Is something like two consumers trying to read the same message same time and trying to commit the offset. And if they are trying to read the same message same, then there could be message duplication, like the same order is being processed twice. That could lead to certain errors as well. So that is something that I would consider as like order, not in a proper order, because we need the first message to be consumed only once, then the next message consumed as second, and then the next message consumed will be third message by any worker. Like, so I so the order thing that comes to my mind is there is a possibility that worker 1 consumes first message and it is taking longer. Then worker 3 comes in and consumes 2 3 4 in a way. And after that, um uh, the worker 1 is just trying to process the first order, like the first message. So like in our accounting book, we might be adding, or like let's say in our backend side, we might be processing second and third first. And then once that, because that is being processed by second consumer, let's say that the second consumer completes whatever process and response that needs to be given for the second and third message. And after that, worker 1 comes back with the response for the first. In such situations, like the order that, like we wanted to preserve the order, right? That has gone wrong, like, so that could be one of the scenarios that comes to my mind. And another could be like the race condition or the duplication part.
That what the race condition and the duplication, like duplication, what did you say? Sorry, I missed it.
So let's say, at the moment, like let's say, both servers come up, like both worker comes up, worker 1 worker 2, we can call them consumer 1 consumer 2. They are trying to read a particular order, let's say order number 1. Now both try to pick into the queue like the first message in the partition they find out is order number 1. They are trying to read it at the same time. So there is no acknowledgement or there is no offset acknowledgement present for that. So both will try to read it. If both will try to read it, then that message is being consumed by consumer 1 as well as consumer 2. They will process and then they will try to commit back the offset, like acknowledge that the message is consumed. And then they try to do it same time, let's say, because both could have the same processing time. If they try to add the offset same time, that means everything is going in parallel. So again the second message will be consumed by both. So if you see, with this way, each message could be consumed twice. That's the kind of um, uh, duplication that's happening. And why the duplication is happening? Because both are trying to consume simultaneously, both are trying to commit the offset simultaneously. Now the offset commit could be like a blocking operation. And then for blocking operation it could try to get the commit, like the hold of the thread that commits the offset. So that is where the rest condition could arise, like both will try to get the lock over the thread that commits the offset.
Okay, I got it.
But that's what we want to achieve, right? We want to consume a single message by the multiple consumers.
No, no.
No,
What
one message, one
do you
consumer.
want to?
Like, yeah, this is what I'm understanding. Correct me if I'm wrong. So we have multiple consumers in a consumer group, and we have multiple partitions. So one consumer is doing some job, consumer two is doing some job, consumer three is doing some job. like how we do in trading. So consumer one is trying to process five messages, the first five messages. Consumer two is trying to process the second five messages. Consumer three is trying to process the rest of the messages. So we want in our service like this. So it's not like two threads should consume the same message, and like yeah, our service will be like two messages we are consuming, and it will not behave right. Like how in this is what I'm understanding in the threading how we do. So yeah, correct me anyone like.
Can you come again? Like I think the
Yeah,
voice
so
like the voice on my side broke, so I was not able to understand.
what I'm trying to tell, like this we can think of like a threading, like how in threading we do, we create 10 threads. First thread do some job, and then second thread do some job, and after then if every thread is done, then we join the threads and we get our work done, and we do parallelize the system so that the faster we can achieve the result. The same thing we can map it here, like consumer 1 and consumer 2. It's like consumer 1 is trying to do some work, and it's trying to process 4 5 messages, and then consumer 2 is trying to messages after then some messages, and trying to do some operations based on that. So two consumers should not be taking one messages uh, from one partition. I mean, you can take it mostly, I don't know, but that is not like the system we want. Like why we want to build a system where the two consumers will be consuming the same message. uh, am I able to explain or?
Yeah, yeah. I think partially you are saying same thing that I was trying to say, but yeah,
Yes, yes, from yours only, like I try to map in the
yeah,
mind. Yeah.
yeah. But that's a like that's the exact use case. As like about this, like in terms of thread, like we need to achieve the thread serializability. In thread serializability, it's like only one thread will try to read the database, or like try to read the message. And if it's the offset is already committed, like only like while committing the offset as well, only one thread will try to commit the offset. So either the message is available for read or committing to the offset. So it's something like read and write sort of an operation. So the race condition here will be one is trying to read and another is trying to write. So that's something like only one should go through. So if the order, if it's not properly serialized, then the possibility is like the first one just tries to read it before the other one is trying to write the offset, and both are consumers of the same consumer group. That means a billing service could read a message twice. That means one order could be processed twice, and that could lead to inconsistencies. Does that help answer your doubt, Nitika?
Asim, can you scroll up a little? I mean, whoever is sharing the screen. Sorry, I mean scroll down. So yeah, if you see here, point number third, that topic A is subscribed by both consumer groups, which means same message is consumed by multiple consumers. So do you mean to say that same messages same message is going to be consumed by multiple consumers of different consumer groups?
Yeah. So same message. We want the same message to be consumed by consumers of different groups, but not the consumers of the same group. Again,
Okay.
consider this like one particular consumer group is mapped to one particular type of service. Like let's say, like billing service and accounting service is a perfect example. One billing service can have 10 workers, right, who are trying to process or divide the share the load in between. Consider one thing, like a simplest example is like this message queue is nothing but a conveyor belt, let's say, okay. and a consumer group is nothing but a worker. Can would you, let's say, and then a message is a packet that is running from a conveyor belt, let's say. So two consumer, like two worker trying to grab the same package, would you want to have two workers trying to grab the same package? Like let's say
No.
two
No.
workers of same department tries to grab the package, read the package, and then like use whatever the information is there. So if two workers of same department or tries to grab the package, possibilities they will duplicate their efforts, right? Let's say that one department is about the billing department. Then let's say one department is billing department and another department is accounting department. You want the info from the package to be read by billing as well as the accounting person. So one person from accounting can come, read the package, and then go away and update its own records. And then another person from a billing department could come, read the package, and then go away. And then since both accounting and billing now have read the package, you are okay to dispose of that package. That's the kind of system that this third bullet point is talking about. But in the following part, in the following paragraphs, what we were talking about is two workers from the billing department itself are trying to compete for that one package. Because and in a way they would be going to do the same thing, same work twice. That would be that would be duplication of the work, right? And in first scenario it was not a
Got it.
duplication of
So how to avoid this race condition?
work. That's what the following paragraph tells about, right?
Okay, okay, I didn't read. Sorry.
So it's nothing but just have one-on-one mapping, just point-to-point mapping. Let's say like one consumer can only consume from one partition. That's it.
Oh yeah, yeah.
So every time consumer number one comes in, it should be routed to, always should be like the request for consuming the message should always be routed to partition one. And every time the consumer two comes in, the request for consumer two should always be routed to partition two.
That mapping where it should be like at the consumer level.
No, it's not on consumer level, it's at the broker level. Broker tries to actually, like, distribute the keys, right? Like the key, consistent hashing part I'm
Yeah, we'll read about it later in the high level architecture.
is it clear, Asim, Nitika, Sandhya?
Yes.
Anyone else has any doubts, like feel free to interrupt me, feel free to let me know.
So Sagar, I had a doubt.
Uh-huh. Go ahead.
One of the part. So when you say it ultimately becomes a one-to-one mapping, right? One partition, one and one consumer of a consumer group, right? So what if the suppose partition one is becomes a hot partition, right? A lot of messages are coming in, and we have only one consumer of a consumer group which is consuming. So that kinds of slows the throughput or like reduces the throughput, right?
Yeah, so that's like basically the downside. And that's a scenario that we need to be aware about. There could be other fault tolerant mechanism that needs to be done, but yeah, that's a potential scenario that
Okay.
definitely happen. That one party, like the hot partitions are due to that only, right? Like
Mm.
this is the exact reason that we have the hot partitions, problem, right?
Okay. Okay.
I think for doing that, we can add multiple consumers. One more consumer you can create, and partition also like we can add, right? Or no? Partition
No,
we can add.
For a queue, consumers is a third party, right? Like, sorry, the outside party, right?
Yeah.
Queue doesn't have any control over consumers, right? Like,
Yes, yes.
it only knows who what all the are all the consumers which are subscribed or registered with the queue. It has no control over the consumers, right? Number of consumers.
That's true.
Sagar, also it can happen that partition one has messages, and consumer one is has a fault and cannot read those or consume those messages. So what will happen in that condition?
Can you come again? Can you come again?
So we have partition one, which is read by consumer one in consumer one group. Okay.
Okay.
So consumer one stops working,
Uh-huh.
but partition one is I mean so consumer one is configured to read from partition one. There is no other consumer who consumes those messages.
Mm-hmm.
So in those conditions, what will happen when the consumer is not able to read those messages?
I think he answers the question, this question in the later part of the
Oh, okay.
chapter.
Yeah, but the simplest answer could be we shouldn't have any problem with that, right? The message will still remain in the queue. That's it. Like,
Yeah,
we
offset
should
will be
not.
there, and when the consumer your consumer comes back, it will read from the same offset. So you should not be having any issue.
So is there any limitation in terms of time, how long the message can remain there, or it?
Yeah, there is usually like the TTL part, and there is a possibility that if the message is not consumed before if before the TTL expires, then the message could get lost. But I think that is again the configuration that we need to do. Like, it depends on the design. So
And yeah, we have already
an outage of
given
a
the
few. Go ahead, go ahead. Yeah, so what I was saying is an outage of a few seconds or few minutes could be acceptable. And if it's something super critical that we need to maintain a high consistency, then we can set up the TTL to be very high, right? Like, and if at all that happens, generally the offsets are committed in batches. Okay. uh, and they tried, if the consumer goes down and comes back, then they try to replay the last batch or couple batches, so that way they can ensure that they have all the messages that have been consumed. Or if any of them are not there, then from the backup storage the messages could be brought back to the queue, and then they could be reconsumed. Okay. I think yeah, then we can read about it in following part. Does that
Anyone else?
answer your doubt, right?
Yes, yes.
Okay.
Anyone else want to read?
I can read. Um, am I audible?
Yeah.
Yeah, okay. So, high level architecture. The below diagram shows the updated high level design. We have producer, brokers, metadata storage, coordination service, and consumer. Clients, producer pushes message to specific topics. Consumer group subscribes to topics and consume messages. So core service and storage, in that we have broker, which holds multiple partitions. A partition holds a subset of message for a topic. The storage, in storage we have data storage, in that messages are persisted in data storage in partitions. State storage. Consumer states are managed by state storage. Metadata storage. Configuration and properties of topics are persisted in metadata storage. Followed by we have coordination service. We have service discovery in that, which tells which brokers are alive. Then we do have leader election. One of the brokers is selected as the active controller. There is only one active controller in the cluster. The active controller is responsible for assigning partitions. So Apache Zookeeper or etcd are the commonly used to elect a controller.
Yeah. So just try to pay an extra attention on the role of a broker. Like all the others are, others would be like pretty much intuitive, except the broker part. Like it holds the multiple partitions, and partition holds a subset of messages for a topic. That means a broker is nothing but a particular machine, and consider one machine is trying to hold 3 4 partitions. Consider a scenario like this. So
Yes.
like whenever any communication happens, the broker will be actually communicating with others, and the partition is actually sitting on top of the broker. So basically partition is an internal component of a broker, but the server itself is called as a broker here.
Yeah, so basically in figure 4.7, we do see those partition 1, 2, those are controlled by brokers, right?
Yeah. uh, I think this is a different one, because they are talking about topic A and topic B. That's why they have like this thing. But yeah, I think possibility is like partition 1 and partition 2 could be sitting on the same broker, or could be
Okay.
sitting on on a different brokers.
Okay. Uh,
And then storage could be just a disk backup or stuff.
yeah, and I think do we need to discuss about the leader election part? I think.
I think at this moment the leader election part could be skipped, because that would be too much of a deep dive.
Okay.
And I think it would definitely come up later. Yeah, but yeah, just the leader is nothing but the controller of like the key space assigning and all sorts of thing. So I think at this moment that could be too much of a detail.
Okay. Do we have enough time to pick up the design deep dive or?
Yeah, yeah,
Um,
let's
okay.
go ahead with that.
Okay, okay. So, design deep dive to achieve high throughput while satisfying the high data retention requirement. We made three important design choices, which we explain in detail now. We chose an on-disk data structure that takes advantage of the great sequential access performance of rotational disk and the aggressive disk caching strategy of modern operating systems. We designed the message data structure to allow a message to be passed from the producer to the queue and finally to the consumer with no modifications. This minimizes the need for copying, which is very expensive in a high volume and high traffic system. We designed the system to favor batching. Small input output is an enemy of high throughput. So, whatever possible, our design encourages batching. The producers send message in batches. The message queue persists message in even larger batches. The consumer fetch messages in batches when possible too. So I think this is pretty straightforward, right?
Yeah, I think the only thing here is the first point where they say we chose on disk data structure that takes advantage of a great sequential access performance of rotational disk, the aggressive disk caching strategy of modern operating system. So I think this is something which is some really low level at this moment. Like even I'm not aware about this great sequential access performance, but this is more like a disk IO, or like how the data is read by the operating system from the disk. So yeah, I think at this moment that could be ignored.
Yeah. Okay. So moving on to data storage. Now let's
Anyone has any doubt up until now? Like,
Yeah, I think these points will be covered later. So, yeah, for now we can skip and then.
Okay.
Data storage will basically cover the first part, and then
Yeah.
later on message data structure, yeah, will be covered.
And also, okay, perfect. Also, one more thing. Does everyone understood this? Small IO is an enemy of high throughput.
No, it will be better if you can explain.
Yeah. So consider like the consumer is coming in trying to like over a network call. The request travels, reaches the broker. It tries to does its job, and just goes back, and then again the response or the message travels over the network and reaches the consumer. This is a typical scenario, and that's happening just for one message, let's say. If that's the case, majority of the response time or majority of the like latency will be spent up over network calls, and very like just a part of it is the like a servicing the request, like on a broker itself, like dequeuing the message, writing the offset. That could be a minority of the work. Majority of the latency could be used by the network calls. If this is the situation, what will happen if we send 10 message or dequeue 10 messages at a time and send them over a network? Then majority of the work would be the dequeuing part, like that be, which like so now like the total network time remains same as for the one message or the batch of message, but now that will be divided by 10 because now 10 messages are being sent over a single network call. So throughput is nothing but total message consumption in a given amount of time, let's say 1 minute. If now we are earlier we were consuming, let's say, one message per minute, now we are consuming 10 messages per 1.2 minutes, or let's say 1.5 minutes. So the throughput itself just like skyrocketed with a factor of 10, or like like somewhat approximately nearly 10.
Oh, that's what the batching it's saying. Like
Yeah.
if you do batching, the high throughput can be achieved.
Yeah.
Thank you.
And then the offset commit also happens in batches. This is an important thing. The reason I am explaining it, this is in, let's say 10 messages are consumed. Possibility is we have the acknowledgement available just 9 of them. There could be a possibility that one of the messages could get dropped, or one of the processing of one of the 10 messages that have been consumed could fail. In that case scenario, the acknowledgement will be given to the 9 of the messages, and the one message which where the acknowledgement is failed could then remain in the queue itself, so that it could be reconsumed by some other consumer or some other call, like same consumer's other call.
Okay.
So one question, Sagar. Since you're talking about that high throughput, we have to have the batch of messages consumed together,
Hmm.
so that um, it becomes efficient in terms of throughput. But what if that there are say we are maybe setting up a parameter for number of minimum number of messages that should be consumed at any point in time. What if there is a delay in number of messages that arrive? Will that create a latency to consume these messages in a batch?
I'm not
So
sure.
what I meant is, say batch, we have configured minimum 10 messages should be there for a consumer to consume. Okay, but at any point in time there are only three. So will it keep waiting for the batch of uh, 10 messages and then only it will consume?
Yes, it will, and then because of that, the latency will increase.
Yeah.
I think so. In that case, a configuration can be made either based upon the size of the queue, or it can be time based. So let's say whatever reaches first, we can start consuming based upon that. If the queue size reaches first, which is of 10, we can start consuming, or we can set up some time, let's say half an hour. If 30 minutes have been reached and there are just three messages, we should be okay to consume those messages.
Okay, got it.
Um, should we start, or like it's already 7? I'm not sure like at what time we stop.
I think we can complete this data storage.
Okay. Okay, so data storage. Now let's explore the options to persist messages in more detail. In order to find the best choice, let's consider the traffic pattern of a message queue. Write heavy, read heavy, no update or delete operations. As a side note, traditional message queue does not persist messages unless the queue falls behind, in which case there will be delete operation when the queue catches up. What we are talking about here is the persistence of data streaming platform, predominantly sequential read write access. So option one, database. The first option is to use a database. Relational database. Create a topic table and write messages to the table as row. Database can handle the storage requirement, but they are not ideal because it is hard to design a database that supports both write heavy and read heavy access patterns at a large scale. The database solution does not fit a specific data usage pattern very well. This means a database is not the best choice and could become a bottleneck of the system. So I think we have been given here the patterns, like three traffic patterns, and we are going to discuss the options. So first is a database. The second one is write ahead log. So I think Sagar, you want to discuss something about like why database is not suitable more in deep, or
Yeah, so actually the traffic pattern are these ones, right? If I'm not wrong.
yeah,
Like
the
the
write
write
heavy,
heavy,
read
read
heavy.
heavy, no update or delete operations. As a side note, a traditional message queue does not persist messages unless the queue falls behind. Um, and then like we are talking about persistence of data streaming thing, and then predominantly sequential read write access. So what they are trying to say here is, like, let's say if we create a database, a topic would be a table, and like the rows would be the messages that we are writing to the table. So the database can handle the storage requirement, but they are not ideal because it is hard to design a database that supports both write heavy and read heavy access patterns. To me this comes out to be something similar to they might be pointing to the SQL database. So in SQL databases, writing is slower and reading could be faster. uh, since we need at a faster rate, like let's say for a very high throughput operation, we need the messages to be written to the partition or the produced to be to the partition very fast, and and be consume at a faster rate. Let's say if that's a scenario, then they say that the NoSQL database will fail because they are slow in terms of producing, like for producing, even though they could be faster in terms of reading. In terms of NoSQL databases, there could be a possibility that the messages would be slower in terms of read, and they could be faster in terms of write. So all sorts of situations could happen. So that's why they are saying that like in terms of latency scale, performance scale, that we are looking for the message queue, any of the databases could fail generally. In any of the operations, databases are considered to be taking are considered to be time consuming. Either they could be time consuming for write operation, or they could be time consuming for read operation. Like there are very few databases like Cassandra, which also has limitations though, um, uh, and which might not be suited for this. We are somehow, like, configured for both read and write heavy traffic patterns. But it still is, like, it still takes a lot of time, then and which creates the bottleneck. Either it could be on a producing time or a consuming time. So that's the reason that database could not be used for storing the messages in a particular partition. So we are actually trying to talk internals of the partition, or let's say internals of a particular queue over a partition.
Okay, any question on this? So option 2, write ahead log. The second option is write ahead log. WAL is just a plain file where new entries are appended to an append only log. Val is used in many systems such as the redo log in MySQL and Wall in Zookeeper. We recommend persisting messages as Wall log files on disk. Wall has a pure sequential read write access pattern. The disk performance of sequential access is very good. Also, rotational disk have large capacity and they are pretty affordable. As shown in figure 4.9, a new message is appended to the tail of a partition with a monotonically increasing offset. The easiest option is to use the line number of the log file as the offset. However, a file cannot grow in infinitely, so it is a good idea to divide it into segments. With segments, new messages are appended only to active segment files. When the active segment reaches certain size, a new active segment is created to receive new messages, and the currently active segment become inactive like the rest of non-active segments. Non-active segments only serve read request. Old non-active segments file can be truncated if they exceeds the retention or capacity limit. So the segment files of same partitions are organized into folder named partition and then followed by partition ID. The structure is shown in figure 4.10. So I think um, it just like we keep appending at the end of the segment, and once that exceeds the maybe configuration or whatever time we have, then that becomes the non-active segment and the active one will be going forward messages will be returned to the active segments, which is a new segment file.
Yeah. So this is a one of the common strategy. So there are something called as a append only log or log structured databases. Log structured databases like these are like a, not a non-conventional database basically, where consider a file. Let's say CSV file. It's comma separated, right? Let's say the first record will be before first comma. The second record will be after the comma. We can keep putting commas like this and keep adding entries to it. So in this case, the adding a new entry is easy. We just put a comma and add the new record and then enclose it with another comma. So in this situation, like the read could be slower, but then that could be processed in between by the folder structure that they are trying to say. Like we can limit the each folder structure by let's say 10 records per folder or per segment and like that. So there could be a binary search that could be applied. So we reach to the folder, which we reach to the intended folder through, let's say, some sort of a binary search or some sort of a resolution. And then once we reach to a proper folder, we can actually sequentially go and reach to that particular message in that folder. Let's say if we are trying to reach the end of the message or the end of the message or the start of the messages over the partition or over the batch. So that kind of structure could yield a faster read write. But one downside is this is specifically optimized for the queue, like the orderly queues. Our any other operation like searching over a large random messages could be tough in this sort of scenario, or it would probably not be even be allowed in this kind of data structure. So whenever we just want to keep adding from front and keep consuming from the back, then these kind of structures could come in. So just an optimized structure for queue kind of like for a queuing pattern or like sequential read write pattern.
So Sagar, in this, I have one question. So non-active segments, as per this, is like non-active segments only serves the read request, right? So in this case, read operation is delayed, right? Because it will have to, the request will have to segregate everything from segment 1 till like maybe segment 3, which is non-active. Is my understanding correct?
No need, right? Like the non-active segment only serve read request. That means like you just read it, and then if the capacity is exceeded and like that, then you just remove it, right? Like the TTL is expired, let's say, then you just remove it, right?
Yeah.
Like what's it out? Can you come again?
Yeah, so I'm actually trying to understand how the read request will be operated in this option. So, for example, we have segment 1 till segment n, maybe, right?
Mm-hmm.
So, how the data will be accumulated from this segments?
So I think, are you trying to ask, let's say we have already read segment 1 till segment 5.
Hmm?
So basically read, while reading, so there'll be latency will be high because again it has to go through segment 1 to segment 5 and then start reading from segment 6. Is that what you're trying to
No,
ask?
I think from segment 1 till segment 5, it will have to append, right? I mean, from 1 till 5. So, that operation will cause some delay.
No, no. I
No?
think look at it in this way. It's a two pointer. Let's say a two pointer pattern or two pointer approach. One pointer is for the write and one pointer is for the read. Okay. So the active partition is will be the one where the right pointer sits right now. So let's say if your active if your right pointer is at segment 2, then it will be pointing to 15th place, right? So whenever you are appending a new message, it will be placed at 15th. And since your right pointer is in the segment 2, you call it an active active segment, because it is active to be written. Once that
Okay.
segment becomes full, let's say you reach 20, then that becomes inactive, and then that just and your right pointer moves to segment 3. So your segment 3 becomes an active segment now,
Okay.
whereas your read pointer will be in the segment 1 one itself, and it will try to read 0 1 2 3 and like that. And read pointer will remain in the inactive segment itself only, because your active segment is being written. Yeah, you can't allow the read pointer to read from the active segment, because that's where the write operation is happening at this moment. So even if you want to put a lock or whatever, you can put it on the active segment.
Okay. Okay. I think, yeah, I understood it. I was taking it as a whole data from segment 1 till segment n, but I think that by that time it has been already consumed by the consumer.
Yeah.
Okay. So I think we are at a note on disk performance. I think I'll read this paragraph, and maybe the message data structure we can pick up tomorrow. But like, yeah, I want to understand from everyone how. Should I read it or?
Yeah, we can read it, at least this one.
Okay. Okay, okay. So, note on disk performance. To meet the high data retention requirement, a design relies heavily on disk drive to hold a large amount of data. There is a common misconception that rotational disks are slow, but this is really only the case for random access. For our workload, as long as we design our on disk data structure to take the advantage of a sequential access pattern. The modern disk drives in RAID configuration, that is, with disk striped together for higher performance, could comfortably achieve several hundreds MB per second of read and write speed. This is more than enough for our needs, and the cost structure is favorable. Also, modern operating system caches this data in main memory very aggressively, uh, s- so much so that it would happily use all available free memory to cache disk data. The while takes advantage of heavy operating system disk caching to as we described above.
Yeah, I think that's about it. Something is about like rotational disk or something like that for I think some we need to read more about this part because this is coming in again and again. So one is rotational disk pattern versus, and then another is sequential access pattern inside the disk. So I think this makes sense because even the operating system reads the memory in a sequential pattern or like block by block. So this is understandable, but what is rotational disk that needs to be understood.
And also, Sagar, like, earlier we discussed about like small input is enemy of the throughput, right?
Mm-hmm.
Somewhere I read that like the situation comes like where the input is smaller, that may cause the random access also, random memory access also. So I want to understand more on that. Looks like this is related.
Sorry, I can you point to the exact one? Like,
Yeah,
because
so earlier I think in this somewhere we read that the smaller input is an enemy of
correct.
the high throughput, right? So
Yeah.
one of the reason is that because smaller input may cause the basically while storing or like if we talk about on the drive level, it may cause like random access memory also. So looks like this is also related like to some disk performance. So can we include that point also?
Yeah, we can discuss about it, but let me try to understand it first. How the small input IO, small IO will affect the performance of the access pattern over a same disk or over a same machine, or let's say random access pattern.
Okay.
Yeah. Okay, I will try to maybe understand it as well because even for me, yeah, I'm trying finding it a bit not relatable, but yeah, let me see. Yeah, we can
Sagar, I
discuss
think
more
it's related to that disk has this mechanical arm, right? So and this it rotates on the sectors, and that's where that moving an arm from one sector to another sector is like it's a bit of a mechanical work, and there it involves random accessing. Like if you want a random access, then from one sector to another sector, the disk arm has to move a bit further. But if it's in the same sector, then the disk will just simply move in that circular motion. So it's not a big movement there. It's related to
oh,
that, I feel. Yeah, yeah.
okay, okay. Like the memory partitioning, you are talking about the memory partitions,
So
like
like
if
for
we
in
are trying to
databases also we have pages, right? So that pages are
page.
stored in disk. So I think it's related to that. Yeah.
Okay, 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 okay. So you mean if we are just loading it one by one, then there could be a high page load yeah, thing, right? Or if we are just loading the pages through batches, then it would be easy,
Yeah,
right?
yeah. So it
Because
will be written into the same sector, so the arm does not have to move further, right?
oh, makes sense. Yeah,
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 yeah.
yeah. So if we are reading it in the batch, then there is a high chance that it could be local, basically localized data versus distributed.
Yeah, yes, yeah, yeah, yeah.
Okay, okay, interesting, interesting. Yeah, I think does that help, Asha?
Yeah, yeah, yeah. Pretty much. Yeah.
Yeah,
I didn't know that it happens this way.
yeah.
Thank you very
It's a
much.
very like yeah, yeah. Thanks. Yeah, that's a very good point. Yeah, I think these are the kind of situations which leads to the corner conditions, like yeah, right over a big
Yeah.
systems like. And then I think, oh, okay. Are you? Is it also about thrashing? They call it usually called as thrashing, right? Or is it related? Like, sorry, my bad. Thrashing is much more related to the page miss. Only if the page is not found or like that. Okay, my
I'm not sure.
bad.
Okay, so I think maybe pretty much we can cover this tomorrow onwards. Message data structure.
Sounds good. Do you guys want to spend some time understanding the right ahead log tomorrow? Like maybe
Yeah,
we
yeah.
can try
I
to
think
find some video and play some video on YouTube, and then I think we can deal with all such doubts that could come up or pop up.
yeah, this will actually basically be helpful in like other things also,
Yeah,
like database internals and other things.
yeah, yeah. And since the same philosophy is shared with the log structure databases as well, right? So yeah, it should be definitely be helpful. Yeah, I think let's try to find a good video, everyone. If we could find it, like try to share it in the group, or maybe we can play it tomorrow.
Yeah. Thank you, everyone. Bye.
Bye.